Thank you, everybody, for joining us this morning in America and this afternoon in Europe. We really appreciate everybody participating today. Broadly speaking, what we'd like to discuss today is opportunities for decarbonization in the chemicals sector. So everybody is very familiar with the burgeoning clean hydrogen ecosystem, but we'd like to use that as a frame of reference and discuss how we can start to electrify chemical and fuel production well beyond applications just related to hydrogen. So quick background on who we are. My colleague Jordan and I are very excited to be addressing you all today. And we both have backgrounds in deep technology. So naturally, that's where we approach these problems from. For the purposes of today, however, think of Jordan as the chemistry and decarbonization guy, and think of me as the engineering and applications guy. And our company, Mattiq, is working to solve many of the challenges you'll hear about today. And of course, feel free to submit questions anytime in the chat. We're happy to address those. And we'll also provide our contact information at the end of the presentation. So please feel free to reach out to us with any and all questions, comments. We'd be happy to set up any follow-up meetings with anyone in the audience. So we have a very diverse audience today, including C-level industry executives, investors, R&D folks, sales and BD people, project engineers, graduate students. And so this is a difficult diversity of audience to satisfy, the deep needs of everybody here. But really, we seek to provide something for everyone. And like I said, if you have questions or want to go deeper on any of the topics with any of us, please feel free to reach out to us. But overall, we want to leave you with a few take-home points. And the first of those is that decarbonizing the chemical sector is a massive economic opportunity. It's not just about decarbonization. There are things that we can do with electrochemistry. We can unlock value in ways that we couldn't do with conventional thermal chemistry. And on top of that, as the price of renewable electricity continues to plummet and it makes up an increasing share of our electric grid, it's clear that decarbonization flows through electrification. And with increasingly cheap electricity, we can make processes that run on electricity cheaper than the status quo. And lastly, early ecosystem formation is going to streamline commercialization in applications beyond clean hydrogen. This clean hydrogen ecosystem that's really starting to hit its stride now has laid a nice blueprint for us in terms of all of the different players that we need to bring together in order to achieve scale and bring new solutions to market. So the agenda for today, Jordan will start us off with a deep dive into decarbonization via electrification across the global economy. And then I'll dive into a few specific case studies about applications in which electrochemistry allows us to do things that thermal chemistry would not have allowed us to do. And then we'll get into lessons learned from the clean hydrogen ecosystem and how we can apply those to more rapidly achieve scale as we bring new solutions to market like those that we'll discuss today. And then finally, we'll wrap up with a Q&A. So with that, I will turn it over to my colleague, Jordan, to get us going.
Yeah, thank you, Mike. And I'm very excited to be here to discuss these important topics with all of you this morning. And so first, I want to set the context for overall emissions throughout the global economy, broken down by sector. Now, when we start to assess which sectors do and do not have reasonably mature decarbonization technologies and paths towards emissions reduction, one thing becomes abundantly clear. Replacing fossil fuels with electricity is the key. Renewable electricity will always be cleaner than fossil fuels, and as renewables become cheaper and cheaper, electricity can and will be more economic than fossil fuels as well. And so, for example, we hear a lot about electric vehicles. We see them all over the roads all the time. And indeed, electric vehicles are poised to make a substantial dent in transportation-related emissions. Additionally, with the increasing fraction of renewable energy within the grid, residential and non-residential building-related energy consumption becomes increasingly green by the day. Even still, these sectors that are at the forefront of really leveraging renewable electricity from wind and solar only represent a fairly small portion of overall emissions. Lots of other areas that are equally important, but considered hard to abate, such as the production of chemicals, fuels, cement, and steel, as a few examples. They're less directly impacted by the boom in renewable power and battery technologies, and therefore require alternative decarbonization or electrification approaches. And broadly, what we'll focus on today is chemicals and fuels and associated challenges and opportunities to reduce or eliminate the 6.3% of global greenhouse gas emissions that the chemical sector is responsible for. So today we're gonna use green hydrogen as a case study and a benchmark for how electrification concepts and technologies can be learned from, built off of, and more broadly applied to decarbonization, specifically within the chemicals industry. As many of you know, green hydrogen, or hydrogen produced from renewable electricity, has seen tremendous growth over the past decade. And we view this massive growth in hydrogen as a precedent-setting technology that we can learn from and build off as we continue to expand decarbonization efforts within the industry. And just for some brief background, the hydrogen markets today are massive, with about 100 million tons of hydrogen produced each year. Yet about 95% of the world's hydrogen is still produced by steam methane reforming. And steam methane reforming alone accounts for nearly 1% of global CO2 emissions, which is a huge number. Yet over the past decade, there have been massive investments from the private sector and from government agencies worldwide to increase the global market share of green hydrogen relative to gray and blue hydrogen, the dirtier forms of hydrogen. And domestically, the US has poured resources into building the hydrogen economy, from infrastructure to technology, with policies such as the Inflation Reduction Act and the DOE's Energy Earthshot program, which highlights hydrogen as one of only 7 critical energy-related technologies for decarbonization. The technology of water electrolysis has a very long history and multiple different flavors. Liquid alkaline water electrolyzers have been in the marketplace for decades, but more recently, proton exchange membrane, or PEM electrolysis, has gained significant momentum and has captured an increasing portion of the global electrolyzer market. A PEM electrolyzer allows for the splitting of water into highly pure oxygen and hydrogen using renewable electricity. And technological advancements over the past decade have, just for example, increased efficiency of electrolyzers, reduced the footprint, and enabled pressurized gas outlet streams, just as a few examples. Yet a few challenges still remain to truly grow green hydrogen to its full potential. And while electrolyzers have become increasingly more efficient and durable, PEM electrolyzers now occupy about 20% of the total electrolyzer market. But these PEM electrolyzers rely on iridium oxide as the anode catalyst. Iridium is extraordinarily rare and expensive, and if the PEM electrolyzer market continues to grow at its current rate, we will simply run out of iridium. And therefore, developing new materials and systems that match the efficiency but reduce the reliance on scarce materials like iridium is critical. And this is actually something we are actively working on here at Mattiq. And secondly, green hydrogen must still compete with gray and blue hydrogen from a cost perspective. And while the so-called green premium is dropping, particularly within green hydrogen, decreasing the cost of green hydrogen is a challenge, but one that can be overcome in a multitude of ways, either by dropping electricity costs or higher efficiencies from the electrolyzers, more efficient catalyst materials, and lower overall CapEx of electrolyzers. And then lastly, not the last challenge we're facing, but the last one I'll discuss today, is that large-scale projects, and I'm sure many of you have seen these in the news, have been announced left and right over the past few years. However, in certain cases, many of them fall short of announced production volumes or never come to fruition at all. And in our view, there appear to be challenges across the value chain, and developing ecosystems to collaboratively bring large-scale projects to market is a challenge that we as a community need to address. And despite these challenges, the hydrogen space has come incredibly far in a very short time period. And the opportunity from both an economic and emission standpoint is enormous. Green hydrogen can deeply decarbonize some of the world's dirtiest processes, including the production of ammonia, fuels, transportation sector, steel, and many others. And the key takeaway here is that it has become abundantly clear that green hydrogen is a priority around the globe, with industry and governments racing to scale the production of green hydrogen. Yet decarbonization within the chemicals industry will require much more than just green hydrogen. And so how can we learn from hydrogen, apply similar concepts and technologies throughout the entire chemicals industry to bring its carbon footprint from 6.3% of global greenhouse gas emissions all the way down to zero? And so today we'll provide our view on how we as an industry can collectively accomplish this. And then we'll bring it to life with a handful of case studies. And so decarbonization of the chemicals industry is so challenging because it is so intrinsically linked to fossil carbon resources, so much so that it is often interchangeably referred to as the petrochemicals industry. And not only is the chemicals industry responsible for 6.3% of global greenhouse gas emissions, but the industry also consumes roughly 5% of global fossil carbon resources each year. When we break down where this 5% goes, estimates vary between about 60 to 70% of those fossil carbon resources are used as a feedstock in the production of chemicals, and about 30 to 40% is used as a fuel to provide energy for performing chemical transformations, separations, etc. Given this massive reliance on fossil carbon, both as a feedstock and a fuel, we must, as a community, identify ways in which we can decouple the production of chemicals from fossil fuels and feedstocks. And what I want you to take away from this slide as I dive deeper into some of these ideas is that the chemicals industry can be decarbonized using renewable energy, just like we've seen in green hydrogen, but it is not a one-size-fits-all solution. It will take a complex and multi-layered technological approach. And so before we dive too deep, there are really three overarching questions that we need to decompose. What is the feedstock? If we're trying to make a material or a chemical, what is the feedstock we start with? What is the driving force of the reaction? And what is the source of the emissions? And depending on the answers to each of these three questions, there are different technological solutions and pathways to reduce the carbon footprint of the chemicals industry. And we've attempted to distill this very complex web of various technological approaches down into a relatively simple decision tree. And so to begin, when considering how to make a chemical or material, we must first determine if the feedstocks can be sourced renewably. And this is the single largest decarbonization opportunity, considering that 60 to 70% of the fossil carbon consumed by the industry is used as a feedstock. So identifying as many possible or as many viable, economically scalable ways to decarbonize high volume feedstocks is a very critical aspect. And so a few examples of this include green hydrogen produced by electrolysis instead of steam methane reforming, syngas produced via co-electrolysis of CO2 and water instead of coal gasification, and leveraging biomass as a feedstock as well. It's just a few examples. And so step two is to then determine, when we're trying to turn chemical or feedstock A into chemical B, can this desired chemical transformation be done electrochemically? And if so, we can power that transformation with renewable electricity, largely eliminating the need for fossil fuels. This represents a major opportunity that we will discuss in much more detail in subsequent slides. And it's also worth noting that in certain cases, electrochemical transformations are already used in industry. For example, the chloralkali process to produce chlorine, a diponitrile synthesis from acrylonitrile, and of course, water electrolysis. And in all three of these cases, these electrochemical processes were initially developed without decarbonization in mind. And electrochemistry was used because of its other advantages, because at the time it was the best way to make those materials. And we will discuss other advantages of electrochemistry in subsequent slides, but the electrification of these existing processes now has the advantage of possible decarbonization using renewable electricity as a convenient side benefit that we're just now starting to take advantage of. And although we would love it if every chemical transformation could be done using electrochemistry, we realize that there are many cases in which it is either not possible or with current technological limitations, it's far from economically viable. And in those cases, we must assess where do greenhouse gas emissions come from during this process. And if the source of greenhouse gas emissions is from the process heat required, we can leverage emerging technologies for renewable process heating. So if the source of greenhouse gas emissions is from using methane or natural gas or coal to heat up a reactor, we can replace those fossil fuels as heat sources with other more renewable technologies. And I mentioned the DOE Energy Earthshots previously, and in fact, another one of the 7 Energy Earthshots is related to this very topic. And there's significant room for more advancement of this technology, including developing resistive electrical heating or even using hydrogen as a heat fuel. On the other hand, if the greenhouse gas emissions stem from the process itself, or CO2 or methane is an actual byproduct of the reaction, then we must use the continually advancing technologies of carbon capture, utilization, and storage to mitigate these emissions. So on this slide, each of the blue boxes represents areas in which we need technological maturation to overcome the deep-seated links between the chemicals industry and fossil carbon. Yet, in many cases, they're oftentimes interconnected. And just as an example, if a reaction produces CO2 as a byproduct, that CO2 can be captured using carbon capture technologies, then valorized using a novel electrochemical process to produce syngas, for example, and then leveraged as a renewable feedstock for the production for different chemicals and materials. And it's these types of innovations that are required for us to reduce or entirely eliminate the 6.3% of global greenhouse gas emissions and the 5% of fossil carbon consumption the chemicals industry is currently responsible for. At Mattiq, we are driving to develop materials and systems that enable novel electrochemical processes or improve existing electrochemical processes. And so for that reason, for the rest of this webinar, we'll focus primarily on electrochemical processes that will play a significant role in the coming decarbonization of the chemicals industry, while we still acknowledge that the electrochemical processes are just one piece of this puzzle for broad decarbonization of the chemicals industry. So next, I will briefly touch on 2 prominent examples of electrolysis beyond water splitting that many of you have likely heard of. And so one of my favorite slogans these days is using the renewable electron as a reagent. And so with the precedent set by green hydrogen, leveraging renewable electrons as a reagent to produce hydrogen, where else can we put renewable electrons to work within the chemicals industry? And so CO2 electrolysis that you see on the left side of the slide leverages renewable electrons to reduce CO2, the most oxidized form of carbon, into useful chemicals and fuels. And it feels like there are hundreds of papers published on CO2 electrolysis every day, indicating that the academic community is clearly engaged in developing this technology and aggressively pushing this area. And in the literature, there are really amazing examples of developing technologies to produce carbon monoxide, syngas, which is a mixture of carbon monoxide and hydrogen, ethanol, ethylene, propanol, and even formate from CO2 via CO2 electrolysis. And in industry, the enthusiasm for CO2 electrolysis is less obvious, but still there. And many startups and even established corporations are entering this space. And for example, Topsoe is doing great work in the commercialization of solid oxide electrolyzers that can produce syngas via water and CO2 co-electrolysis. Other companies such as 12, Air Company, and many others are aiming to commercialize this technology as well. And the outlook of CO2 electrolysis at present is still unclear, as the technology readiness and resulting economics have many unanswered questions. Yet the efforts within the community and the potential benefits of this technology are apparent. And similarly, on the right side of the slide, nitrogen reduction to produce electrochemical ammonia comes in a very close second place in the total occupancy of my Google Scholar notification inbox, indicating that academics and startups are really pushing this technology to decentralize and electrify the production of ammonia. And the societal and environmental impacts of a high TRL nitrogen reduction electrolyzer would be profound. And so both of these problems are very hard, but there are tons of people out there working to solve them. And the impact of each technology from an emissions perspective would be astronomical. And sticking to the theme, despite the fact that large-scale commercialization of either of these processes has yet to be for the last decade. And without the revolutionary work done in hydrogen fuel cells and water electrolyzers at places like GM, Los Alamos National Lab, NREL, and many others, it's difficult to imagine that these related electrolysis technologies would be as advanced as they are. And so beyond hydrogen, CO2 reduction, and ammonia synthesis, what else can we do? Where else can electrosynthesis have a massive impact? And outside of decarbonization, what are other reasons, or what other reasons may there be to use electrolysis more broadly? And we see electrification as the future of chemicals and fuels production. While thermochemical reactions will always have a place in the chemicals industry, we see electrochemistry as a hugely underrepresented technology within the industry. And beyond water electrolysis, CO2 electrolysis, and ammonia production, we anticipate many benefits of electrifying other, more targeted chemical transformations as well. On the right side of the slide, you see just a few of the potential benefits of electrosynthesis as compared to traditional routes. Existing industrial electrochemistry processes have set this precedent. And now it is on us as a community to identify and pursue the opportunities in which we can reach these 5 benefits within non-traditional electrochemical processes. And so now I'll finish there. I'll turn it back to Mike, who has a few case studies that are emblematic of these 5 key benefits. And I would also like to remind everyone to submit any questions or comments in the Q&A.
All right. Thank you, Jordan. So I know Jordan just threw a lot of information at you, and my apologies in advance for throwing a lot more information at you over the next couple of slides. But as he mentioned, there are some key benefits of electrochemistry as compared to conventional thermal chemistry. And I'd like to dive into a few specific case studies that explain each of the 5 benefits on the right-hand side of the screen in a little more detail. So first, we'll discuss the importance of selectivity in chemical processes. And what I mean by selectivity is the ability to manipulate molecules in the way you want while avoiding side reactions that you don't want. And so we'll discuss that today in the context of sustainable aviation fuel. So sustainable aviation fuel, or SAF, is a rapidly growing market that aims to decarbonize aviation. So of course, with aviation, we can't decarbonize that sector just by battery powered vehicles like we can with ground transportation. And the production of sustainable aviation fuel is primed for explosive growth, as aided by the US Inflation Reduction Act, which provides a $1.25 per gallon tax credit, which is quite significant. And today, SAF is primarily produced from plant oils and restaurant grease using a process known as the HEPA process, hydroprocessed esters and fatty acids. So while this is a technologically mature process, that relies on feedstocks that can only serve about 10% or less of the aviation industry as a whole, particularly as demand for aviation fuel continues to grow in the coming years. And so it's really the lack of selectivity in the processing abilities of hydrocarbons that precludes diversification of SAF feedstocks that could allow us to achieve scale and then serve the entirety of the aviation fuel market. And so this is where electrochemistry can come in. And specifically, what we can do with electrochemistry is the selective transformation of short chain carboxylic acids into paraffins. So what does that really mean? If we look on the bottom left of our screen here, we've got a few carboxylic acids, short chain hydrocarbons that can be sourced from biomass waste or fermented food waste, for example. And then utilize a process called Colby coupling that can convert those carboxylic acids selectively into paraffins, getting us much closer to the desired end product of jet fuel. And so what's actually happening in this chemical process? We have these carboxyl group on the end of our hydrocarbons that can be selectively removed, and then those two distinct hydrocarbon chains can be coupled together to form a long chain hydrocarbon. And so typically, long chain hydrocarbons like this can only be sourced from fossil fuel feedstocks, but here electrochemistry shows us a pathway that can enable us to diversify the feedstocks that can be used to make sustainable aviation fuel. And so if we think back to Jordan's decarbonization decision tree from a few slides ago, what we're doing here is using renewable feedstocks. So that was his first question. And then two, electrifying the process that enables us to get to that end product. And by the way, we have a side benefit of using electrochemistry in this case, where in any electrochemical reactor, we have two electrodes, the anode and the cathode, where oxidations and reductions take place. And in this case, at the anode, we're producing that paraffin product like we discussed, but at the cathode, we're actually taking advantage of extra hydrogen that's involved in our system. And so we can actually produce useful hydrogen as a byproduct of this chemical process, allowing us to add even more value to this system. All right, moving along. So with that selectivity in mind, next we'll discuss how electrochemistry can improve the processing of toxic gas H2S. So as a quick backgrounder here, we have to remove sulfur from fossil fuel feedstocks to prevent downstream SOx emissions. And we typically do this with hydrogen. So hydrogen extracts the sulfur from this sour gas or crude oil, but this results in significant production of H2S, which is a highly toxic gas. So we can't just vent this to the atmosphere. We have to process it. And conventionally, we use what is known as the Claus process, which first fully oxidizes that H2S to sulfur dioxide in very high temperature reactors, exceeding 1,000 degrees C typically. A second step then will convert that sulfur dioxide to elemental sulfur at about 300 degrees C. But that 1,000 degrees C step is really the problem here, where if we think back to Jordan's decarbonization decision tree, that process heat can be very carbon intensive. And in fact, about 2% of global fossil fuel demand comes from chemical process heat. And so it's reactions like this that are the source of needing those fossil fuels to run burners and get to these very, very high temperatures. So what can we do instead? We can think about H2S conversion electrochemically near ambient conditions to make hydrogen and sulfur. So what does this really allow us to do? This is the reduction of H2S to sulfur. And then at the other electrode, we are producing hydrogen. So this allows us to do two things. One is avoid that very carbon intensive first step of the reaction. So we can avoid entirely that 1000 degrees C thermal step. And secondly, instead of wasting that hydrogen that's present in our system and producing water, what we're doing instead is extracting value from the system by producing hydrogen. And so we can either use that clean hydrogen for on-site applications, so consider that a regeneration of that hydrogen that we can then use to further extract sulfur from our fossil fuel feedstocks, or sell that clean hydrogen out into the broader market. So ultimately, thinking back to the decision tree here, we're doing two things. We're electrifying this chemical process, and we are avoiding process heat that would be ordinarily needed. All right, our next application will explore the value of producing chemicals at the point of use and enabling us to design more efficient supply chains. And the example we'll use here is hydrogen peroxide. So this is a large market as it stands today. Hydrogen peroxide is typically used for pulp bleaching for a diverse array of paper products, as well as for wastewater treatment. And its use cases are actually expanding as it's increasingly viewed as a green oxidant for more chemical processes beyond these initial ones. However, the conventional production of hydrogen peroxide leverages the anthraquinone process, which requires large centralized production facilities that allow us to achieve the economies of scale needed to make the numbers work. It also uses a high temperature synthesis process in organic solvents. And because we are producing hydrogen peroxide at centralized facilities, we need to transport it then to where it's actually needed. But concentrated hydrogen peroxide is an explosion risk. And so it must be diluted to about 10% or less in water for safe transportation. But this presents a fairly large problem where we either have to ship trucks around that are mostly composed of water with dilute hydrogen peroxide, or we have to just bolt on a very large hydrogen peroxide production facility next to those pulp bleaching plants, for example. But often this results in way too big of production of hydrogen peroxide compared to what is actually needed. So ultimately, either way, we have an inefficient supply chain and production process associated with this conventional anthraquinone process. So instead, what we can do is electrochemically produce hydrogen peroxide from water and air instead of from fossil fuel feedstocks. What this also allows us to do is achieve positive economics at smaller scales. And so that enables us to deploy modular, right-sized reactors that produce hydrogen peroxide at the point of use. So we can produce exactly how much peroxide we need at the location that it's needed. So this then allows us to eliminate supply chain inefficiencies associated with shipping around truckloads, mostly of water. So then thinking back again to this decision tree, we are using renewable feedstocks instead of fossil fuel feedstocks and using electricity to power this process. All right, hope everyone's still with me. So if you'll recall again from Jordan's presentation, direct emissions refer to those that result from the chemical process itself, not from the heat or feedstocks needed to run the process. And so specifically here, what we'll take a look at is oxygenate production. which accounts for nearly 30% of chemical industry emissions. And so some examples here are ethylene glycol and ethylene oxide, among others, where the thermal conversion, say, of ethylene to ethylene oxide often leads to an over-oxidation of hydrocarbons, resulting in conversion of ethylene to CO2, for example, instead of ethylene to ethylene oxide. And due to this thermal process, we can lose up to about 20% of that ethylene feedstock that we fed into the reactors and lose that to CO2. So we're wasting valuable feedstock. Instead, we can employ electrochemistry to do selective oxidations of these hydrocarbons into oxygenates. And so we mentioned selectivity earlier, and it comes into play again here, where these selective oxidations allow us to avoid those direct CO2 emissions and ultimately eliminate a very large chunk of CO2 emissions to the tune of hundreds of millions of tons of CO2 per year based on these processes alone. And again, we can observe something really interesting about electrochemistry, where we have two reactions happening in the same reactor. And so the bottom left example shows us that in propylene to propylene oxide conversion, we again have extra hydrogen in our system that can be used to produce usable hydrogen. And so again, we're adding value at both electrodes. And as a result of this, we can start to think about really interesting chemical plant design, where we can couple these reactions in such a way that that hydrogen can then be used at a different place within this same chemical plant, reducing the amount of other hydrogen that you need to create from either steam methane reforming or water electrolysis. So it's reactions like this that can really boost the efficiency of chemical plants. And I'd also just like to mention that Ted Sargent, who's on our scientific advisory board, recently wrote a really, really nice overview paper of this kind of process. And so we're excited to be working with him as well. All right, so for our final case study, I'll be talking about cost. So to achieve scale, ultimately, we need to bring down the cost of production of an electrified process to be below that of the status quo. And specifically, what we'll be discussing here is polyethylene terephthalate, which is one of the world's most important plastics, very ubiquitous for use in things like plastic water bottles. So today, PET is produced from paraxylene primarily, which inherently ties it to fossil fuel feedstocks. It'd be very difficult to source that paraxylene from renewable feedstocks. So instead of thinking about making PET in a different way, what we can do instead is develop an alternative chemical analog to PET, which is more recyclable, has a lower carbon footprint, and can be cheaper to produce. And so that alternative is PEF, or polyethylene furanoate, which is a close chemical cousin to PET, it has many of the same properties. So we've seen actually market validation for PEF with Avantium constructing a PEF production plant. However, they use a thermal process to produce this PEF, or rather its precursors, whereas electrochemistry can be used to drive down costs and carbon emissions even further. So specifically, what we're looking at is the electrochemical oxidation of a common biomass processing byproduct to make that PEF monomer. And so if you'd like to discuss this application in more detail here and get into all the chemical structures, Jordan and I would be happy to follow up with anybody to dive in deeper on this application. But suffice it to say, this is another example where we can add value at both electrodes and produce not just that valuable PEF precursor material, but also hydrogen at the other electrode. So this is a very common theme in electrochemistry and an alternative way to make clean hydrogen as well. So today, PEF, this PET alternative, can be produced at a slight premium compared to PET, but recent techno-economic analyses show that with the right electrochemical system, PEF production can be beaten by PET production costs can be beaten by PEF production, substantially reducing the carbon footprint and costs associated with this material. And so again, this is a significant decarbonization opportunity, both in the use of renewable feedstocks and an electrified chemical process. Okay, so that wraps up our case studies. I know I went through them quickly, so I hope they made sense. And like I said, happy to dive in deeper about any one or multiple of those with folks in the audience today. All right, so we'll wrap up here by discussing the burgeoning clean hydrogen ecosystem, which has laid a really nice blueprint for how we can bring new solutions to market and achieve scale. So this is a very complicated ecosystem. You know, if we've learned anything from clean hydrogen ecosystem development, where the technology developers are worried about better and cheaper catalyst materials, better membranes, better stack designs. The manufacturers are concerned about sourcing materials at scale and driving down the learning curve. The project developers are worried about securing long-term contracts, both on power acquisition, but as well as on feedstock. You know, it's quite complicated. And then the operators are concerned about the long-term durability and reliability of these systems. And finally, off-takers are pulling demand all the way through this system. And this is all happening under the rapidly evolving regulatory environment where things like the US Infrastructure Bill and the Inflation Reduction Act are providing incentives on the onshored manufacturing of electrolyzers, but also on the production of clean hydrogen itself. But there's a lot of questions that are still being answered, say on how are we sourcing the electricity used for that clean hydrogen production? And so it's been a very interesting past couple of years, and we look forward to seeing where this industry goes from here. But as we expand beyond clean hydrogen, how can we learn lessons from that first iteration and accelerate new solutions to market that go beyond hydrogen, like the ones we've discussed today? So specifically, the technology developers will be thinking about new high-impact opportunities and developing holistic electrochemical systems and catalyst materials that will enable the efficient production of new chemicals and fuels from electrically driven processes. Manufacturers, as always, will be concerned about manufacturing at scale at low unit costs and navigating the supply chain constraints associated with the key materials they need. Project developers will be acquiring renewable power at low costs, designing projects to maximize value add, and making sure all the numbers work for these processes. And then operators minimize electricity costs always, make efficient supply chains like the ones we discussed with hydrogen peroxide, for example, and maximizing system lifetime. And ultimately, off-takers will be concerned about the carbon footprint of the products that they're actually purchasing. And so our objective really is to bring all of these different players together, including government, to make sure that we streamline commercialization and accelerate these very exciting new solutions to market. So with that, I'd like to leave you with 3 key takeaways before we jump into a quick Q&A session here. We have a major opportunity at our hands, and this is not just about decarbonization, although we can address a significant portion of global emissions through the chemical sector alone. But this is also an economic opportunity where electrification enables us to run chemical processes and supply chains more efficiently so that we can cut costs and carbon. And like I mentioned, you know, we can do things with electrochemistry that we could not do with thermal chemistry, unlocking new avenues for value add. And finally, if we leverage the lessons learned from clean hydrogen so far, we can accelerate new electrochemical solutions to market that leverage renewable feedstocks and really drive that carbon footprint of the chemical sector close to zero. So thank you all for your attention today. Thanks for sticking with us. We really appreciate that. Our emails are both listed here on this slide, so please feel free to reach out with any questions you have. We're happy to dive in deep on any of these discussions. We're obviously quite excited about all of the opportunities here. On top of that, we are hiring, so please reach out if that is of interest to you as well. So thank you again for your attention, and we'll conclude with a few questions here. Jordan, if you want to lead the charge there.
Yes, absolutely. I will also note that our job openings can be found on our LinkedIn page, but also feel free to reach out to either of us if you're interested in learning more. So we have a bunch of questions in the Q&A, and Mike, I'll let you take a breath for a moment, and I'll take a stab at the first one. So what aspects of electrosynthesis technology are most lacking for implementation beyond hydrogen, CO2, and ammonia? And so I think this is a really important question. And there's multiple aspects, and I'll just touch on a few. And in my view, I think the most important thing that we as a community need to do is identify the highest impact opportunities within electrosynthesis. So, we provided 5 case studies today, but there are almost certainly many, many more opportunities that make sense from both a technological standpoint and an economic standpoint. And really from there, from an actual real deep technology perspective, we need to start kind of from the base of all of these applications. So how can we actually develop catalyst materials to selectively perform industrially relevant transformations with high selectivities that is competitive with thermochemical processes? How can we design reactor architectures to maximize current density or product formation and minimize byproducts? Also, we need to consider things like, what are the byproducts, and do they make separations more costly and more difficult? But really, I think the most important thing in my mind is identifying those opportunities and demonstrating that they can be performed at current densities and selectivities that will make them competitive with thermochemical processes, while keeping all of these, from the very beginning of the technology development, keeping in mind the fact that we need to scale and manufacture these reactors to make them mean anything to the industry at the end of the day. And so that's my brief answer to that question. Mike, if you have anything to add, feel free. Otherwise, we can tackle the next one.
Yeah, the only thing I'll add is to echo your comment about the manufacturing as well, where the at-scale manufacturing of water electrolyzers and fuel cells that's happening today will certainly lay the foundation for the next applications in manufacturing these reactors at scale.
Right. Okay, Mike, I will tee this next one up to you. So what you care about is not renewable sources of electricity, but sustainable and clean sources of electricity, such as nuclear, right?
Yeah.
I would say I have to agree with that. Renewable is always great, but sustainable and low carbon footprint is really a key aspect to make these technologies truly decarbonizing throughout the industry.
Yeah, with nuclear, of course, is a zero carbon electricity source. And so, as we start to evaluate the carbon footprint of the chemicals and fuels that we make using electrically driven processes, nuclear certainly would score well, but we'll also follow the guidance of the US government as well as we continue to develop the incentives for clean hydrogen production, and specifically, the rigorous tracking of where electricity came from in order to produce hydrogen. We'll follow the guidance in terms of how they classify nuclear as far as production goes of hydrogen.
Okay, Mike, another one for you. So what are some of the CapEx or infrastructure challenges
All right. I think I knew where that question was going, but it looks like you froze there, Jordan.
Oh, did I cut out? Okay, let me
Yeah,
repeat.
CapEx and
What are
infrastructure challenges.
so challenges associated with the transition from a thermal process to an electrochemical process at a commercial scale?
Yeah, absolutely. So, of course, any process that runs specifically on electricity is going to require a pretty significant load. And so the power grid infrastructure at any of these chemical plants, it's something that will need to be closely looked at. So, the load at a typical chemical plant is going to be in the tens of megawatts. And so a reactor, an electrochemical reactor at scale, is also probably going to be in the tens of megawatts range. And so the development associated with hooking up to the power grid infrastructure and securing reliable, low cost, and in particular, low carbon sources of electricity is going to be an ongoing challenge. And so electricity procurement is a major part of this industry moving forward, especially as we seek to track where that electricity came from to ensure that it was indeed clean.
Yeah, and one thing I'll add to that is that in an ideal world, swapping out a thermal process for an electrochemical process, a lot of the downstream purification processes hopefully will be very similar. Of course, that will be case by case, and I think hard to know exactly what all the challenges will be. And those are really specified to each process. But I think the purification and processing infrastructure after the crude product leaves the reactor, hopefully there will be lots of overlap. Okay, next one. So Mike, I'll start with this one and maybe you can add. So in your proposed biomass to PEF process, how do you deal with biomass preparation for the electrochemical cell, diversity, cost, and impurities? And so one of the things I'll add here is that there have been really tremendous efforts throughout the industry in utilizing biomass to make highly pure feedstocks sourced from biomass. And so, for example, the actual precursor that's involved in the process we discussed it's chemical called HMF. And there are already large plants that are producing that directly from biomass. But this is a challenge as we seek to diversify what we can actually source from biomass that a lot of people are tackling, and there's lots of government funding going into that topic, and it's a complex challenge, and one that needs to be considered, especially if we're going to be using biomass sourced feedstocks in electrochemical processes.
Yeah, I think you nailed it there.
Okay, I think we probably have time for one more. And so let's go with, let's see. So what are the limitations of this new technology, and what needs to happen for legacy companies to go through this transformation if the old way of doing things is still highly profitable?
Yeah, it's a really important question as we move forward here. And so really, our objective is to start by identifying where there are acute pain points in the status quo. And so if we approach the market that way and we use electrochemistry to uniquely solve problems that can't be solved the conventional way, that is our route in. That's our way to crack the market. Even if, petrochemical processing is still profitable, it's not that it's perfect in every way. And so if we start by attacking where there are legitimate, real problems faced by chemical plant operators, then we can successfully crack that market.
Yeah, I think that's a very good point. And I think, initial demonstrations to prove the viability of this replacement of thermochemical processes will then give more solid footing for the next application and the next and so on. And to address what are the limitations of this new technology. And so we don't know is the answer. And it's in many cases, there's hardly any work done either in academia or in industry to actually electrify certain processes. And so what are the limitations? And I think that's one of the exciting parts, at least from my perspective, is that we don't really know what the limitations are. But we're fairly confident that we have yet to reach those limitations with most applications that we discussed and many others. And so I think that probably we're just about out of time. And so I think we'll wrap it up there. We will be happily reach out and respond to the other questions that we didn't have time to get to today. And I want to thank everybody again for joining us. It was really great, putting all this together. And we're really excited about the opportunities ahead of us.